Hi, I'm here to present Falcon, which predicts the cache performance of a given program quickly, accurately, and incrementally as you update the program. Okay, so why do we even want this? Well, if you want to optimize some program where, let's say, there's some two kernels that the input goes through, and you're considering like which of two optimizations to apply, like maybe either fusing or tiling, you need some kind of cost model which allows you to pick the better one. So many optimizations focus on memory performance. So in this paper, we focused on that. And yeah, maybe if you could somehow predict what the miss rate would be, cache miss rate would be after applying each of these, then maybe you could pick the better one. And in particular, we want to focus on analyzing the cache performance of huge programs, like let's say neural networks. They have like many different phases, and each of so here we have what's called connext neural network, and each block inside it has like a bunch of additional kernels, and like let's say you want to optimize one in particular, and you want to ask like, okay, how does this change performance of the whole thing? If you had to run this whole like forward pass of connext in the large setting, like profiling it takes like 70 minutes. And you would hope to do it much faster with analytical modeling, but the state of the art cannot scale to these huge programs and actually ends up being slower. But we are able to do it pretty quickly, and that's what we'll go into now, how to do that. So we model SRU caches. So least recently used cache. So I'll quickly go through what it is. I assume people are kind of familiar with it. But yeah, as you access A, B, C elements, these elements come into the cache, and when you access an element that's already in the cache, then it sort of comes to the front. And if you have to get rid of some element because the cache is full to insert a new one, then the one that was accessed least recently will get eliminated. And that's it. That's what a least recently used cache is, and you can sort of like analyze this. So the elements that are in the cache are always the last n that you accessed, unique locations that you accessed, and here like the size of the cache is 3. And yeah, a miss occurs in exactly one of two scenarios. One is if you access something for the first time, so that's called a compulsory miss. And the other is if you did access it earlier, but the last time was a long time ago. And what do we mean by long time? The sort of metric that matters here is how many unique memory locations have been accessed since the last time that the same location was accessed. So here it's 2, and the cache size is 3, so it's a hit. But if it was 3, with the cache size of 3, then it's a miss. And the way the model is going to work is by sort of creating an analytical formula that models this distance. Okay. The state-of-the-art model, how they did it was they sort of computed these dependencies because we had to find the last time the same location was accessed. That's basically a dependence. You don't have to worry about these formulas. But basically, like what I want to tell you is that they used all these like sort of operations to create some kind of formula which captures the dependence. But unfortunately, when you do these things, it doesn't scale very well with the size of the input formula that you give. And therefore, if you want to analyze a very large program, like say a neural network, then this stuff doesn't scale very well. So that's what we want to focus on, how to scale this. So actually, like what we want to do is just dependence analysis. So we use like the existing algorithms for polyhedral dependence analysis, which can give you the same result, but much more efficiently for large programs. So let's look at an example. Here, like for 0 to 499, we're accessing A at I, and then B at I, and then C at I, and C again. And then C at 0, B at 400. And A at some X, let's assume it's like something you don't know, but it's in bounds. Like I'll tell you why we need that later. But anyway, so you just run like a dependence analysis algorithm on this thing. It will tell you immediately that like all the accesses in the first 3 loops have no dependence. So it's like a compulsory miss because they're accessing those for the first time. And if we look at this C0, we will get a dependence to this statement at iteration 0, and then B to iteration 400 of that loop, and A, we would get a dependence to some iteration of the first loop. And I won't go into the details of how to sort of compute the distances and so on, but basically you will get 499 unique memory accesses between C0 and iteration 0 of that loop. So that 499 is the distance, and let's assume that the cache size was 512. Then this would be a hit because 499 is less than 512. For B, it would be 500 because of these loops. Both of these loops combined access only like 500 unique elements because C is repeated. And then iteration 400 of that loop has 99 after it, so 599 in total, which is more than the cache size. So you get a miss. And the interesting part here is for A, even though like we don't know which location is accessing, we still know it's going to be a miss for sure, because like we have the B and the C loops in between, and even if you don't really look into which iteration the dependence goes to, you still know that there's at least 500 plus 500, so 1,000 unique elements accessed in between by these loops, which is more than 512, so it's a miss for sure. And this is what we're going to exploit to do some optimizations here. So even if I change this last first loopness at the top to maybe be in reverse or add some other statement or whatever you do, it doesn't matter. It's always going to be a miss. So we don't even need to look at that loop nest. So what this means is when we're doing this kind of dependence analysis, that if there was some dependence that was really far away, then in general dependence analysis, we would have to go all the way there to find out what the exact dependence is. But here, because in this particular application domain, we only care about finding out whether it's a hit or a miss. So we want to find out if it's near or really far. And so that means that in a practical program, you only really need to look, like a couple of loopness above for each sink, for each statement that you're trying to analyze. So that's one optimization. And this kind of principle will immediately also lead to being able to do incremental updates of the analysis. Because as we just saw, no matter what changes we do to the first loop over there, the last statement is always going to miss. So what does that mean? Let's say that the user made some kind of modification to this first loop. Then we can sort of start computing this distance metric downwards. So after this, for B loop, there's 500 unique accesses. After the C loop, there's 1,000. And we know that this 1,000 is greater than or equal to 512. And that means that everything after this sort of line in the program is always going to have the same cache performance as before, no matter what modifications you do to that first loop. So now that means that if you change that loop, then you only need to recompute results for the next two loops after it. And the whole rest of the program can just inherit the results that you computed earlier. So here, for example, in the C loop in the gray box, its dependence goes to the C loop right above it. And so its distance is not in any way affected by the modifications that you did to anything above that. And similarly, the C0 also has a dependence in the unmodified region and also the B400 axis. So since all of these dependencies and distances are sort of within code that is the same as it was initially, they're going to have the same cache performance as before. Now, the A thing is a little bit different. It does have a dependence potentially in a modified region, but it doesn't matter because, like we saw earlier, it's too far away. So it's going to be a miss no matter what you do in that loop. So basically, if you modify the first loop, you only need to recompute results for the modified loop, of course, and two more loopness after that. So that means that, again, in practice, sort of like there's like a constant number of loops that you have to recompute for, which means that it ends up being much faster than it would be to compute for the whole program. Okay, so now let's look at an experimental evaluation of the performance. So the previous models had always focused on what's the Polybench benchmark, which has many small programs. So each is like basically one loop kernel, maybe matmul or Floyd washer or something. They have like sort of complex code structure, but the size is small, and that's the reason that these previous tools like didn't really need to think about scaling. So we made a new benchmark consisting of like convolutional neural networks, like standard ones like AlexNet and ResNet and many others, and sort of like these neural networks are much bigger than like the single kernel benchmarks, and because of that, they like being faster on these requires like different optimizations, and we saw that the previous state of the art haystack is actually like really slow on many of these huge networks. So this is a linear scale, it's hard to see, so let's make it log scale. And so Falcon runs in less than 5 minutes on all of these, whereas we run with like a 4-hour timeout because otherwise, it takes forever. So haystack hits this timeout very often, and we always run within 5 minutes. And because the dependence analysis thing that I just talked about is sort of separate for each statement, so it's like embarrassingly parallel, and you can trivially parallelize it, whereas the haystack approach of sort of computing those operations on the formulas is not as, cannot really be parallelized. So with parallelism, we get even more speed up. And for to evaluate the incremental computation, we sort of like look at an average across the program of, we look at each statement and we consider if this were updated, then how long would it take to recompute the analysis incrementally. And this gives like a further 100x, actually 133x speed up beyond recomputing for the whole program. And on top of this, we have some improvements to accuracy as well. So the way haystack worked is there's some approximations made to like sort of simplify the analysis and make it practically feasible. So if you had to figure out, so until now I've been talking about elements being in the cache, but actually in practice you have what are called cache lines, and each cache line has, let's say, 8 elements. Then to find out which cache line is hit by some array access, you have to basically do this computation. So the base address of the array plus, like the linearized access expression. And then you need to float divide by 8 because there's 8 elements in each line. And this float division and this expression is kind of complicated, and so it can end up being slow in practice. So what they do is sort of do some kind of padding, where firstly let's assume that the base address is aligned, and now sort of pad the last dimension so that the expression simplifies. So once you pad one of the dimensions, then everything else becomes a multiple of 8 and it goes out. Basically, they sort of have to pad the last dimension to 8. And that seemed to work okay for them in Polybench maybe, but like in convolutional neural networks, for example, and probably many other applications, the last dimension can be really small. So if you pad it to 8, then it makes a big difference. So we may do a slight modification to this where we look for a sufficiently big dimension and pad that. And that actually makes a pretty big difference to accuracy, at least on the benchmark of CNNs. The previous approach had a correlation of around 0.56 to between hardware measured cache miss rate and the predictions. And for us, we get 0.98, which is, I would say, pretty accurate. And yeah, so to conclude, Falcon is fast, more accurate, and can incrementally update computations. Thanks.
Very good, thank you. Questions, come up to the microphone.
Hey, it was a really nice talk. So I had a question. So you said that the analyzed cache properties are inherited by the blocks below. So like, how do you do that? Like, you look at the dominating blocks and only inherit for those blocks, or it's more like based on control flow?
Yeah, so we didn't go into those details here because the benchmark is like sort of straight line code with just loopness. So
Okay, you don't
yeah, we
need
just
to.
literally look at it like serially below in this.
And in the loop nest, if the iteration counts is unknown, like the trip count is not known, so in that
Oh, no,
case,
it
will it
has to
still
be
work?
known.
Okay, it has to be
It has to be
specifically
known. I mean, in the neural network benchmark, like the sizes are fixed and everything is fine. So
Okay, so it's
yeah,
not.
if it's not known, then you can't do it.
Okay, thank you.
And neither can any previous model either.
Okay, thank you.
Well, you mentioned Falcon is multi-threaded, but do you consider multi-thread programs? Do you assume the cache may be polluted by other threads? I mean, do you model it?
Oh no, we can't model multi-core. Like we can't model shared caches.
I
It's
see.
single core.
Are there existing works that do it? Are you aware of?
Not at least not in polyhedral
I see.
models. Like it's really hard and it's also non-deterministic. So yeah.
Nice talk. How much did the hardware prefetching interfere in your evaluation?
So the measured miss rate is for a PMU event, which is basically we are trying to. It only refers to the L2 accesses. I think that the prefetching is not counted in that event. Like, that's what I believe. Yeah.
Thanks for nice talks. And I have some questions from the implementation aspect. And because during the compilation, the compilers may do some like loop unrolling and instruction reordering to improve the performance. And I would like to know if the analytic model is still applicable after the interactions done by the compiler, and what's the interplay between the analytical model and the compiler's optimizations?
Yeah, so we implemented this in the MLI framework. So like you would have to, you would have to give the model the program after you've done the optimizations. So I don't know if that answers your question or what is your question?
Yes,
Okay.
thank you very much.
Okay, thank you again.
Thanks.